The story of our universe is, in many ways, a story of awakening. For countless millennia, humanity looked to the heavens and saw only a tapestry of silver points on a black canvas, a beautiful but seemingly unchanging backdrop to our worldly dramas. Yet, in the last few centuries, and with breathtaking speed in the last few decades, our perception has transformed. We have learned to see the stars not as distant lights, but as suns, each one a potential anchor for worlds of its own. We have discovered that our own star, the sun, is but one of hundreds of billions in a vast, swirling city of stars we call the Milky Way galaxy, and that our galaxy is itself just one of perhaps 2 trillion such islands in the observable cosmic ocean. It is a realization of scale so profound that it borders on the incomprehensible, a stage of such magnificent proportions that it seems impossible for it to host only a single, lonely actor. This shared sense of wonder at the cosmos is something that connects us all, and we invite you to tell us where you are listening from and what time it is for you in the comments, and to subscribe so you are notified of future stories. The mathematical logic seems inescapable. With hundreds of billions of stars in our galaxy alone, and with the discovery that planets are not the exception, but the rule, there should be billions of worlds capable of bearing life. If even a tiny fraction of those developed intelligence, our galaxy should be humming with activity. A vibrant, interstellar community of countless civilizations. Yet, when we turn our most sensitive instruments to the sky, when we listen with our electronic ears for the faintest whisper of a distant conversation or the stray signal of a far-off technology, we are met with nothing. The heavens are profoundly, unnervingly silent. This chasm between the logical expectation of a universe teeming with life and the stark, empty reality we observe is the heart of a deep and unsettling cosmic mystery. It is a question that, once asked, is impossible to ignore. If the universe is so vast and so old, where is everybody? To truly grasp the weight of this question, we must first embark on a journey of scale, an attempt to wrap our minds around the sheer immensity of the cosmic stage upon which our small human drama unfolds. For most of our history, this stage was believed to be small and intimate. The Earth was the center of everything, and the stars were mere decorations, fixed points of light in a celestial sphere that revolved around us. This cozy, human-centric view began to crumble just over 4 centuries ago, when pioneers of astronomy turned their newly invented telescopes to the heavens and began to map the true geography of the cosmos. What they initiated was a progressive and often shocking dethroning of humanity from its self-appointed central role. Our planet was revealed to be just one of several worlds orbiting our sun. Our sun, in turn, was found to be a rather ordinary star, lost in a crowd of countless others. This crowd of stars is our home galaxy, the Milky Way, a structure of such colossal size that its reality stretches the limits of human imagination. From a great distance, it would appear as a luminous, spinning pinwheel, a flattened disk of stars, gas, and dust, with a dense, glowing bulge at its center, and elegant spiral arms curling outwards. This disk measures approximately 100,000 light years from one edge to the other, a distance so vast it translates to roughly 950 quadrillion kilometers, or about 590 quadrillion miles. Even its thickness is staggering, averaging about 1,000 light years, or 9.5 quadrillion kilometers, which is nearly 6 quadrillion miles. Within this colossal structure, our sun and its family of planets are not centrally located, but are residents of a quieter suburban neighborhood. We drift through the Orion Arm, a minor spur of a spiral arm, about 27,000 light years from the galactic core's chaotic and brilliant heart. The sheer size is only one part of the equation. The other is the population. The precise number of stars within the Milky Way is impossible to count directly, but based on its mass and luminosity, astronomers estimate that our galaxy contains somewhere between 100 billion and 400 billion stars. To put that number into perspective, for every single human being alive on Earth today, there are at least a dozen stars in our galaxy alone. It is a number that dwarfs the grains of sand on all the world's beaches. For centuries, this was a tantalizing but purely philosophical idea. The 16th century Italian philosopher Giordano Bruno famously speculated that these distant stars were suns just like our own, each attended by its own retinue of worlds, a belief that contributed to his tragic execution for heresy. For 400 years after him, the existence of these other worlds, or exoplanets, remained a matter of pure conjecture. We could see the stars, but any planets orbiting them would be far too small and dim to detect directly, lost in the overwhelming glare of their parent suns. It was a technological challenge akin to trying to spot a firefly hovering next to a searchlight from dozens of kilometers or several miles away. But in the late 20th century, astronomers developed ingenious new methods to find these hidden worlds indirectly. One of the most successful is the transit method, which involves monitoring a star's brightness with incredible precision over long periods. If a planet's orbit happens to carry it directly between its star and our telescopes, it will block a tiny fraction of the starlight, causing a minuscule periodic dip in the star's observed brightness. It is a dip so small that it is often less than 1 part in 10,000. But with sensitive enough instruments, it is a clear and unmistakable signature of an orbiting world. Another powerful technique is the radial velocity method, which watches for the subtle gravitational tug a planet exerts on its star. As a planet orbits, it pulls its star back and forth ever so slightly, causing the starlight to shift minutely towards the blue and red ends of the spectrum, a wobble that betrays the presence of an unseen companion. The floodgates of discovery were opened by missions like NASA's Kepler Space Telescope, an instrument launched in 2009 with the sole purpose of staring at a small patch of the sky containing over 150,000 stars, patiently waiting for the telltale dimming of a planetary transit. The results from Kepler and other subsequent surveys have been nothing short of revolutionary, exceeding even the most optimistic predictions. They have transformed exoplanets from a theoretical possibility into a statistical certainty. As of our current time, astronomers have confirmed the existence of well over 5,000 planets beyond our solar system, with thousands more candidates awaiting verification. We have found a bewildering variety of worlds, massive gas giants larger than Jupiter, orbiting scorching hot, perilously close to their stars, known as hot Jupiters, rocky super-Earths, several times the mass of our own planet, and even planets orbiting two stars at once, like the fictional world of Tatooine. But the most profound insight gleaned from this torrent of data is not just that exoplanets exist, but that they are ubiquitous. The statistics suggest that planetary systems are not a rare exception, but a normal and common outcome of star formation. On average, there is at least one planet for every star in the Milky Way. This means our galaxy is home to not just hundreds of billions of stars, but also hundreds of billions of planets. The cosmic stage, we have learned, is not empty. It is cluttered with worlds. This realization brings us to the next crucial step in refining the great question. While it is fascinating to know that there are hundreds of billions of planets, the real issue for the search for life is how many of these worlds might be habitable. This led astronomers to define a concept known as the habitable zone, more colloquially called the Goldilocks zone. It describes the orbital region around a star where the temperature is neither too hot nor too cold, but just right for liquid water to potentially exist on a planet's surface. Water is the key ingredient because, as far as we understand it, it is the universal solvent essential for the complex chemistry that gives rise to life. Here on Earth, wherever we find liquid water, from the deepest ocean trenches to the interiors of rocks in arid deserts, we find life. While life elsewhere could theoretically be based on a different chemistry, water is a fantastically effective medium for biochemistry, and it is cosmically abundant. So the search for life as we know it begins with the search for liquid water. Planets too close to their star will have their water boiled away by the intense heat, leaving a parched, sterile surface like Venus. Those too far away will be frozen solid, their water locked up in impenetrable ice, like the moons of Jupiter and Saturn. The habitable zone is that temperate, celestial sweet spot in between. The size and location of this zone depend on the star itself. A hot, bright star will have a habitable zone that is farther out and wider, while a cool, dim red dwarf star will have a much closer and narrower one. By combining the data on the prevalence of planets with the characteristics of different star types, scientists can now make a robust statistical estimate of the number of potentially habitable worlds in our galaxy. They focus on finding planets that are roughly Earth-sized, as a planet that is too small cannot hold on to a substantial atmosphere, and one that is too large tends to accumulate a thick, crushing gas envelope like Jupiter, making it inhospitable to surface life. The current estimates, while still being refined, are staggering. A 2017 study using data from the Kepler mission suggested that there could be as many as 10 billion potentially habitable Earth-sized planets in the Milky Way galaxy alone. Some more optimistic analyses place this number as high as 40 billion. Even using the most conservative figures, we are left with a galaxy that contains unusual billions of potential cradles for life. The raw materials and the right conditions appear to be commonplace. The stage is not just vast. It is filled with an astonishing number of potential sets, each one a world of rock and water, orbiting a stable star, basking in just the right amount of warmth for life's chemistry to begin. And our galaxy is just one of trillions. If even a minuscule fraction of these worlds, say 0.01%, were to actually develop life, and a similarly tiny fraction of that life were to evolve intelligence and technology, there should be hundreds of thousands, if not millions, of technological civilizations in our galaxy right now. Many of these would be far older and more advanced than we are, having had a head start of thousands or even millions of years. For such a civilization, spreading across the galaxy would be a relatively straightforward, if lengthy, endeavor. Even with technology we can envision today, using spacecraft that travel at a fraction of the speed of light, an advanced civilization could colonize the entire Milky Way on a timescale of a few million years. This may sound like an eternity to us, but on the cosmic calendar, which spans more than 13 billion years, it is a mere blink of an eye. The fact that the galaxy could be crossed so quickly, cosmically speaking, is what gives the paradox its sharp teeth. So we are left with this stark and deafening contradiction. The evidence of our telescopes and the logic of our mathematics tell us that the sky should be full of signals, that the galaxy should be, if not bustling, at least showing some signs of other technological inhabitants. Yet we see nothing. The Grand Theater is perfectly appointed. The potential actors are numbered in the billions, and the play has been running for eons. But as we look out into the cosmic audience, we see only empty seats. This was the landscape of astronomical knowledge, a universe pregnant with possibility but barren of proof, that set the stage for a simple, almost casual lunchtime conversation in the middle of the 20th century, where a brilliant physicist would distill this vast cosmic uncertainty into 3 unforgettable words. That simple conversation took place in a setting that was itself a testament to humanity's recent and explosive technological prowess: the Los Alamos National Laboratory in New Mexico. The year was 1950. The world was still emerging from the shadow of the Second World War, a conflict that had been ended, in no small part, by the work done in this very place. Perched high on the Pajarito Plateau, a landscape of stark, sun-beaten mesas and deep canyons over 2,200 meters, or about 7,300 feet, above sea level, Los Alamos was a city born of secrets. During the war, it had been the clandestine heart of the Manhattan Project, a hastily constructed community where some of the world's most brilliant scientific minds were gathered to unlock the power of the atom. By 1950, the frantic urgency of the war had subsided, but the intellectual intensity remained, now redirected by the chilly political winds of the burgeoning Cold War. The physicists, chemists, and engineers who walked these halls were the new high priests of a technological age they had personally inaugurated. They lived in a surreal world, a blend of mundane suburban life and research so advanced it bordered on the metaphysical, all set against the dramatic backdrop of the Sangre de Cristo Mountains. Into this unique environment walked a man who perfectly embodied its spirit of brilliant pragmatism: Enrico Fermi. Born in Rome in 1901, Fermi was a true prodigy, a physicist of rare and dual talents, equally gifted in the abstract realms of theoretical physics and the hands-on realities of experimental work. His colleagues in Italy had nicknamed him the Pope for his perceived infallibility in physics. He had earned the Nobel Prize in 1938 for his work on induced radioactivity, but his journey to Stockholm to accept the award was a ruse. With his wife, Laura, who was of Jewish heritage, Fermi and his family did not return to Benito Mussolini's Italy, where anti-Semitic racial laws had just been passed. Instead, they fled directly to the United States, an escape that would profoundly alter the course of history. In America, Fermi's genius was quickly recognized, and he became a central figure in the Manhattan Project, overseeing the work that led to the world's first self-sustaining nuclear chain reaction at the University of Chicago in 1942, a critical step towards the atomic bomb. Fermi was known for his grounded, approachable nature, a stark contrast to some of his more eccentric colleagues. He possessed an uncanny ability to find simple, elegant solutions to bafflingly complex problems, often through what came to be known as Fermi problems, quick, back-of-the-envelope calculations based on estimation and logical assumptions. He could, for example, famously estimate the number of piano tuners in Chicago with surprising accuracy, using nothing but a series of reasoned guesses about the city's population, the number of households, the frequency of piano ownership, and the work schedule of a typical tuner. This was the mind, practical, quantitative, and deeply curious, that turned its attention to the stars during a short walk to lunch one summer day. He was accompanied by 3 of his colleagues, Emil Konopinski, Herbert York, and Edward Teller, men whose names were also destined to be etched into the history of the 20th century. As the 4 physicists strolled under the bright New Mexico sun towards the Fuller Lodge, the historic log-built heart of the laboratory community, their conversation was light and topical. It was not of nuclear fission or global politics, but of something far more whimsical that had recently appeared in the popular press. The late 1940s and early 1950s were the dawn of the flying saucer craze. The famous Roswell incident had occurred just 3 years earlier in 1947, not far away in the same state of New Mexico, and reports of mysterious objects in the sky were becoming a national fixation. The conversation that day was sparked by a recent cartoon published in the New Yorker magazine by the artist Alan Dunn. The cartoon playfully addressed the spate of flying saucer sightings by depicting small, alien figures diligently emerging from their landed spaceship, carrying trash cans, which they were carefully emptying into a New York City receptacle. The joke was simple. These mysterious visitors from another world were the ones responsible for a recent series of unexplained disappearances of public trash bins. The scientists, men who dealt daily with the frontiers of the possible, were amused. They began to chat about the cartoon and the broader subject of unidentified flying objects. The conversation naturally turned to the physical plausibility of such events. They jested about the obvious explanation that the UFOs were piloted by aliens, and then, in their characteristic way, began to dissect the physics of the idea. Edward Teller, a man who would later become known as the father of the hydrogen bomb, brought up the daunting challenge of interstellar travel, questioning whether it was possible to exceed the speed of light. The discussion was casual, a momentary diversion for minds accustomed to grappling with the fundamental forces of the universe. For a time, Fermi himself remained quiet, letting the conversation flow around him. He smiled at the jokes, but did not actively participate in the debate. But as his friends talked, his mind was already at work, performing one of its famous mental calculations. The topic of aliens and interstellar travel was, for him, not just a source of amusement, but a quantifiable problem. A puzzle that could be estimated and analyzed. In his mind's eye, he began to lay out the variables. He started with the age of the galaxy, a vast expanse of time. he considered the sheer number of stars, the hundreds of billions we now know to be there. He estimated the fraction of those stars that would likely have planets orbiting them. He then narrowed the field, guessing at the percentage of those planets that would fall within a habitable zone, possessing conditions suitable for life to emerge. From there, he considered the probability of life actually starting on such a world, and then the likelihood of that life evolving intelligence. He added another factor, the fraction of intelligent species that might develop advanced technology capable of interstellar communication or travel. And finally, he factored in the lifespan of such a civilization, the window of time during which it would be active on the galactic stage. He was, in essence, mentally sketching the very probabilistic argument that would later be formalized in the Drake equation. He multiplied these estimates together, one after another, in a cascade of logic. Even using what he considered to be conservative numbers at every step, the final result was unequivocal and astonishing. The number was not 1 or a dozen or even 1,000. His quick calculation suggested that our galaxy should be home to a vast number of advanced extraterrestrial civilizations. Furthermore, given the age of the galaxy, many of these civilizations would be billions of years older than our own. If even a handful of them had undertaken interstellar travel, they would have had more than enough time to spread across the galaxy, exploring, colonizing, or at the very least, leaving some unmistakable sign of their existence. Their radio signals should be crisscrossing the cosmos. Their probes should be in our solar system. Their settlements should be on nearby worlds. The evidence of their presence should be obvious and overwhelming. It was at this moment, as the four men sat down for their meal in the bustling dining hall of the Fuller Lodge, that Fermi broke his silence. Abruptly, seemingly out of nowhere, he looked up from his thoughts and asked a simple, piercing question that cut through the lunchtime chatter. "But where is everybody?" The question hung in the air. Konopinski, Teller, and York were initially taken aback, unsure what he meant. Then they immediately understood the full, profound weight of his words. He was not asking about the other diners in the lodge. He was asking about everyone else in the entire galaxy. He had performed a calculation that showed the universe should be teeming with intelligent life, and he was pointing out the glaring, absolute lack of any evidence for it. The logic was so direct, the conclusion so clear, that the absence of evidence became a paradox. The great silence of the universe was not just a lack of signal. It was a contradiction. The rest of the lunch was spent in a flurry of speculation, as the physicists, prompted by Fermi's question, began tossing out possible explanations, the very same hypotheses that scientists still debate today. Perhaps, they suggested, interstellar travel is simply too difficult or too expensive for any species to undertake. Or maybe advanced civilizations invariably destroy themselves in nuclear wars before they can colonize the stars. a particularly poignant thought for the men who had built the first atomic weapons. Maybe we were the first, the earliest civilization to arise in the galaxy's long history. Or perhaps they had come and gone long ago, leaving behind only inscrutable ruins we have not yet found. That lunchtime question, born from a newspaper cartoon and a brilliant mind's habit of a calculation, was never published in a scientific paper or delivered in a formal lecture. It was an off-the-cuff remark. Yet it has echoed through the decades, becoming more powerful and more perplexing as our knowledge of the universe has grown. It perfectly framed the tension between the statistical likelihood of alien life and the observational reality of its absence. It transformed the search for extraterrestrials from a fantastical dream into a genuine scientific problem, a puzzle that challenges the very foundations of our understanding of life, intelligence, and our own place in the cosmos. It was the first informal step in trying to bring structure to the grandest question of all. The next step would require a more formal approach, an attempt to write down Fermi's mental calculation as an equation that could guide the search. That formal approach would arrive just over a decade later, not in the high-security confines of a nuclear weapons laboratory, but amidst the tranquil, rolling hills of rural West Virginia, a place chosen for its profound and deliberate quiet. This is the home of the National Radio Astronomy Observatory at Green Bank. Established in the late 1950s, it is a sanctuary for listening, a place where enormous steel dishes are tilted towards the heavens, straining to catch the faint cosmic whispers that have traveled for eons across the void. The site was chosen precisely for its isolation, nestled within a government-mandated National Radio Quiet Zone, a vast area of some 34,000 square kilometers, or 13,000 square miles, where earthly radio transmissions are heavily restricted by law to prevent interference with the sensitive work of the telescopes. Here, in this valley of silence, a young and visionary radio astronomer named Frank Drake was embarking on a quest that many of his peers considered to be, at best, a fringe pursuit, and at worst, a complete waste of precious telescope time. Drake was consumed by the very same question that had troubled Fermi, and he was determined to move it from the realm of lunchtime speculation into the domain of observational science. In 1960, he conducted the first modern experiment in the search for extraterrestrial intelligence, or SETI. He called it Project Ozma, a whimsical name borrowed from the ruler of the fictional land of Oz. For several weeks, he used the observatory's 26-meter, or 85-foot, telescope to listen intently to two nearby sun-like stars, Tau Ceti and Epsilon Eridani, hoping to detect the telltale signature of an intelligent, non-natural radio signal. The project detected nothing, but it was a landmark beginning. The first time humanity had systematically applied its technology to the search for others. Drake's pioneering work earned him the respect of a small but growing circle of scientists who believed the question of extraterrestrial life was worthy of serious inquiry. To foster this nascent field, it was decided to hold a small, informal conference at Green Bank in the autumn of 1961. The goal was to bring together a handful of the best minds from various disciplines to discuss the prospects for finding intelligent life beyond Earth. The guest list was small, only about a dozen people, but it was eclectic and brilliant. It included the young astronomer Carl Sagan, whose future work would bring the wonders of the cosmos to millions. The neuroscientist John Lilly, who was famous for his controversial research into dolphin communication and consciousness, and the biochemist Melvin Calvin, who had just won the Nobel Prize for his work on photosynthesis, the very process that powers most life on Earth. As the organizer of the conference, Frank Drake was faced with a challenge: how to structure the discussion. The topic was so vast, so filled with unknowns, that the conversation could easily devolve into a series of disconnected and inconclusive debates. He needed a framework, an agenda that would guide them logically through the problem. A few days before the meeting, as he was preparing his opening remarks, he decided to break down the grand, central question: what is the number of detectable civilizations in our galaxy, into a sequence of smaller, more manageable pieces. He realized that the problem could be expressed as a single chain of probabilities, a series of terms multiplied together, each one representing a critical step on the long evolutionary road from a simple star to a communicative civilization. He scribbled the idea down, refining the terms. What he created was not a complex physical formula, but a simple, elegant piece of probabilistic logic. When the conference convened in November, Drake walked to the blackboard and, for the first time, wrote out the 7 terms of what would forever be known as the Drake equation. He began not with planets or with life, but with the fundamental building block of the cosmos: stars. The first term, which he labeled R star, represents the average rate of star formation in our Milky Way galaxy. It asks a simple question: how many new, viable suns are born each year? This is the ultimate font from which all potential worlds must spring. The second term, FP, is the fraction of those stars that have planets. In 1961, this was a complete unknown, a matter of pure conjecture. Some astronomers believed planetary systems, like our own, were exceedingly rare freaks of nature. Drake and his colleagues, however, took a more optimistic view, and history has proven them right. This term acts as the first major filter, narrowing the pool of stars to only those that host other worlds. The third term, NE, focuses the search further. It represents the average number of planets within a given planetary system that have an environment suitable for life. This is the concept of the habitable zone we explored earlier, the orbital region, where a planet could possess liquid water on its surface. This term transforms the raw count of exoplanets into a more meaningful number, the tally of potentially habitable worlds. With these first three terms, Drake had defined the number of suitable stages for life to appear in the galaxy each year. But a stage, no matter how perfectly set, is not the same as the play itself. The next terms of the equation made a courageous leap from the certainties of astronomy into the vast, murky waters of biology and sociology. The fourth term, FL, represents the fraction of those habitable planets on which life actually arises. This is perhaps the most profound unknown in the entire equation. Is the leap from non-living chemistry to a living organism, a process known as abiogenesis, a common and almost inevitable outcome given the right conditions? Or is it a fantastically improbable fluke, a 1 in a trillion accident that happened on Earth, but perhaps nowhere else? We currently have only one data point, our own planet, making any estimate little more than a guess. Assuming life does arise, the fifth term, FI, asks what fraction of that life goes on to develop intelligence. Life on Earth existed for over 3 billion years as simple, non-sentient organisms like bacteria and algae. It is only in the last geological eye blink that a single species, humanity, developed the kind of abstract technological intelligence the equation is concerned with. This term forces us to consider whether intelligence is a convergent evolutionary trait, a path that life frequently discovers, or an evolutionary accident of staggering rarity. The sixth term, FC, adds another crucial filter. It represents the fraction of intelligent species that go on to develop a technology that is detectable across interstellar space. An intelligent species of aquatic creatures, for example, might have complex language, philosophy, and culture, but they would be unlikely to build radio telescopes. This term specifies that the civilization must not only be smart, but must also become a broadcaster, intentionally or otherwise sending signals out into the cosmos. Finally, after this long cascade of probabilities, Drake arrived at the seventh and final term, the letter L. It stands for the length of time, in years, that a communicative civilization survives and continues to broadcast its presence. This variable shifts the focus from the origin of life to its longevity, and it is, in many ways, the most sobering part of the equation. A civilization might overcome all the astronomical and biological hurdles only to be undone by its own success. Does the development of technology inevitably lead to self-destruction through nuclear war, environmental collapse, or some other unforeseen catastrophe? Or do successful civilizations overcome these challenges and endure for millions of years, becoming stable long-term members of the galactic community. This final term, L, acts as a multiplier, not of space, but of time. A galaxy filled with 1 million civilizations that each last for only a few hundred years would be largely silent, their signals appearing and disappearing like fleeting sparks in the dark. A galaxy with just a few thousand civilizations that each last for millions of years would be a much more vibrant place, with a higher chance of 2 or more being active at the same time. The product of these 7 terms would yield N, the number of detectable civilizations in our galaxy right now. Drake never intended his equation to be a tool for getting a precise answer. He knew then, as we know now, that the values for most of the terms are complete unknowns. Its true genius lies not in its answer, but in its structure. It is a powerful organizational tool, a way to break an impossibly large question into a series of smaller, more focused questions. It is a roadmap for our ignorance, showing us exactly what we need to learn to find the answer. For the rest of the conference, the dozen scientists debated the values of each term, plugging in their own optimistic and pessimistic estimates. The final answers for N varied wildly, from as low as 1, meaning we are alone, to as high as many millions. The exercise demonstrated that the Fermi Paradox was not a simple matter of a single missing piece, but a complex puzzle involving astronomy, geology, biology, and sociology. The Drake equation codified Fermi's lunchtime napkin math, giving it a formal language and a clear structure. It provided the intellectual backbone for the entire field of SETI, a field dedicated to turning the unknown values of the equation into known quantities, and in doing so, transforming the great cosmic silence from a philosophical mystery into a solvable scientific problem. And one of the most compelling and potentially chilling proposed solutions to this problem reframes the entire question. It suggests that the silence we observe in the universe is not the result of a single missing variable in an equation, but the signature of a vast, unforgiving obstacle course that lies between the formation of a habitable planet and the emergence of a galaxy-spanning civilization. This concept, formalized in the 1990s by the economist Robin Hanson, is known as the Great Filter. The hypothesis posits that in the long, arduous chain of evolutionary events, there must be at least one step that is astronomically improbable, a barrier so difficult to overcome that it effectively filters out almost all potential life from ever reaching a technologically advanced stage. The chilling beauty of this idea is that it forces us to confront a profound and unsettling question about our own existence. Where are we in relation to this filter? Have we, humanity, already passed it, or does it still lie in our future? If the great filter is in our past, then the silence of the cosmos is not a mystery to be feared, but a testament to our own extraordinary rarity. It means that We are the lucky ones, the winners of a cosmic lottery on a scale so vast it defies imagination. It implies that at some point in our 4 billion-year history, life on Earth navigated a bottleneck that has stopped life everywhere else. If this is the case, then what could that filter have been? The first, and perhaps most fundamental candidate, is the very beginning of the story, the origin of life itself. We call this process abiogenesis, the transition from inanimate chemistry to a living, self-replicating organism. On the primordial Earth, some 4 billion years ago, the oceans were a warm, dilute soup of complex organic molecules, a rich chemical playground energized by lightning, volcanic heat, and the harsh ultraviolet radiation of a young sun. But the gulf between a soup of amino acids and even the simplest living cell is wider and deeper than we can easily comprehend. A living organism is not just a bag of chemicals. It is a fantastically complex information processing system. It requires a molecule, like RNA or DNA, capable of storing a blueprint, and a mechanism for accurately replicating that blueprint. It needs a metabolism, a way to draw energy from its environment to power its operations. And it needs a container, a cell membrane, to protect its internal machinery from the outside world. How these 3 essential components came together in a single coordinated system remains one of the greatest unsolved mysteries in all of science. It is entirely possible that the precise sequence of chemical events required to spark life is so staggeringly improbable that it has happened only once in our entire galaxy. If this is the great filter, then the universe could be filled with billions upon billions of beautiful, habitable worlds that are completely sterile. They may have oceans, continents, and atmospheres with all the right chemical ingredients, but they remain nothing more than lifeless chemical laboratories where the spark of life never ignited. The silence we perceive would be the default state of the cosmos, and our living world would be an almost miraculous exception to the rule. But what if the origin of life is not so difficult? What if, given the right conditions, simple life is a cosmic inevitability? If that were the case, our galaxy might be teeming with microbial life, a cosmic ocean filled with bacteria-like organisms. The great filter must then lie at a later stage. A powerful candidate for this next barrier appears about 2 billion years after life first emerged on our planet. For an immense stretch of geological time, life on Earth was stuck in a rut. It consisted entirely of simple, single-celled organisms known as prokaryotes, a category that includes bacteria and archaea. While incredibly successful and adaptable, these organisms are fundamentally limited in their complexity. Then, in a single transformative event that appears to have happened only once in Earth's history, a new kind of cell was born, the eukaryote. The eukaryotic cell is a marvel of biological engineering, vastly larger and more complex than its prokaryotic ancestors. It contains a central nucleus to house its DNA and a host of specialized internal structures called organelles that function like miniature organs. The key to this leap in complexity, according to the theory of endosymbiosis, was a freak accident of consumption. One simple cell attempted to devour another, but instead of being digested, the smaller cell survived inside its host. Over countless generations, this internal resident evolved into the mitochondrion, the powerhouse of the cell, providing it with a massive surplus of energy that prokaryotes could only dream of. This single chance encounter, a failed meal that became the most important partnership in the history of life, unlocked all the potential for large, complex organisms. Every plant, every animal, every fungus, every creature on Earth, more complex than bacteria, is a eukaryote. If this singular, unrepeated event was the great filter, then the universe might be full of slime worlds, planets covered in microbial mats that thrive for billions of years, but never evolve beyond that simple stage. The galaxy would be alive, but it would be a silent, unthinking kind of life, incapable of ever building a telescope or pondering its place in the cosmos. Even if life begins and complex cells evolve, there are further hurdles on the path to a technological civilization. The development of multicellularity, sexual reproduction, photosynthesis, all represent significant evolutionary innovations that could potentially act as filters. Yet, many of these innovations have occurred independently multiple times on Earth, suggesting they may not be improbable enough to be the great filter. This leads us to another, perhaps more humbling possibility. The filter could be the evolution of intelligence itself. Specifically, the human-like intelligence capable of abstract thought, complex language, and technology. For hundreds of millions of years, Earth was dominated by the dinosaurs, magnificent creatures that were the undisputed masters of their world for a reign 150 times longer than our own species has existed. Yet, for all their success, they never developed a civilization. Intelligence, as we understand it, is not necessarily the ultimate goal of evolution. An organism needs only to be smart enough to survive and reproduce in its environment. On our own evolutionary branch, the path to our specific kind of intelligence was long and circuitous. It likely involved a rare confluence of factors: a primate body plan with opposable thumbs for tool use, a shift to a diet rich in energy that could fuel a large and costly brain, and the complex social structures that drove the development of sophisticated language. Perhaps the precise evolutionary pressures that forged the human mind are so unique that they have never been replicated anywhere else. In this scenario, the galaxy could be filled with vibrant, complex biospheres, worlds with jungles, oceans, and savannas teeming with a rich diversity of life. There might be countless planets with their own versions of dinosaurs, insects, and fish, but without a single species ever making the leap to build a fire, invent a wheel, or contemplate the stars. The silence, in this case, would be the sound of a universe full of life, but a universe devoid of anyone to talk to. If any of these past hurdles is indeed the great filter, it means that our presence on this small, blue planet is the result of a chain of luck so long and so improbable that we are, for all practical purposes, alone. The empty sky is not a puzzle, but a reflection of our own status as cosmic survivors, the children of a billion cosmic miracles. This is, in a way, a hopeful thought, for it implies that the great danger is behind us, but it carries with it a profound sense of responsibility. If we are the only thinking beings in a galaxy of 400 billion stars, our future is not just our own, but the future of all the consciousness the galaxy may ever know. It is a lonely and monumental thought, but it is dwarfed by the terror of the alternative, the possibility that the silence is not behind us, but is instead a grim forecast of what is yet to come. This alternative is the most unsettling and humbling of all the proposed solutions to the great cosmic silence. It is the hypothesis that the hardest step on the ladder of cosmic evolution is not the origin of life, nor the development of complex cells or intelligence. Instead, it is the step we are on right now. This is the theory that the great filter lies not in our distant past, but in our immediate future. In this sobering view, the universe may indeed be filled with nascent civilizations. Life may be common. Intelligence may arise on millions of worlds, and countless species may look up at their own stars and begin to build the first tools of technology. But there is a hidden, nearly universal barrier that prevents these burgeoning civilizations from surviving long enough to make their presence known on a galactic scale. The silence of the cosmos, then, is not the sound of an empty nursery, but the eerie quiet of a galactic graveyard, filled with the ghosts of civilizations that reached our level of development, and then, invariably, failed to proceed any further. The implication is terrifyingly simple. We are not special because we are the first, but because we might be next to fall silent. This future filter would not be an external cosmic threat like a stray asteroid or a nearby supernova, which are too random to be a truly universal barrier. Instead, the filter is likely to be an intrinsic consequence of technological advancement itself, a self-imposed trap that is almost impossible to avoid. The most classic and visceral candidate for this future filter is the one that haunted the minds of Enrico Fermi's generation: nuclear self-annihilation. The discovery of how to split the atom represents a profound and dangerous turning point for any intelligent species. In a single stroke, a civilization gains access to a source of energy that is almost limitless, a power that could fuel its expansion to the stars. But the very same physical principle grants it the ability to destroy its entire biosphere in a matter of hours. The moment a civilization invents nuclear weapons, it starts a clock ticking on its own survival. It enters a period of intense technological adolescence, possessing the power of a god, but not necessarily the wisdom to wield it. Humanity entered this perilous phase in 1945, and for the next several decades during the Cold War, we teetered on the very brink of this filter. In October of 1962, during the Cuban Missile Crisis, the entire fate of our species rested in the hands of a few individuals in Washington and Moscow. For 13 agonizing days, a global thermonuclear war was not just a possibility, but a palpable probability. Had events unfolded slightly differently, had a single command been misinterpreted, or a single moment of panic prevailed, our civilization would have ended, leaving behind a poisoned, radioactive planet that would slowly erase all traces of our existence. It is not difficult to imagine this same drama playing out on countless other worlds. Any species with a history of tribalism, competition, and warfare, upon discovering nuclear power, would face the same existential test. If even 99.9% of civilizations manage to navigate this crisis, but that remaining 0.1% destroys itself, that could be enough to explain the silence. But nuclear war is only the most dramatic of the potential self-inflicted apocalypses. A more insidious and perhaps more likely filter is one we are wrestling with today: ecological collapse. The Industrial Revolution that powers a technological civilization is, by its very nature, an extractive process. A species learns to burn fossil fuels, clear forests, and mine its planet's crust for resources, all to fuel its accelerating growth. For a time, this seems like a path to prosperity. But the planet is a closed system, and the civilization's own waste products begin to accumulate, altering the very chemistry of its atmosphere and oceans. This could lead to runaway climate change, where a planet's temperature rises beyond a critical tipping point, triggering feedback loops that render it uninhabitable. An increase of just a few degrees Celsius, a mere handful of degrees Fahrenheit, could be enough to cause catastrophic sea level rise, extreme weather, global famine, and the collapse of the ecosystems upon which the civilization depends. The filter, in this case, is a race against time. The civilization must recognize the danger and transition its entire global energy and economic system to a sustainable model before it irretrievably damages its only home. The cruel irony is that the civilization's success is the very thing that sets the trap. The more successful and expansive it becomes, the more energy it consumes, and the greater the strain it places on its biosphere. If the transition to sustainability is too slow, or if political and economic inertia prevents meaningful action, the civilization simply exhausts its planetary resources and collapses under the weight of its own metabolic waste. The silence we observe could be the sound of millions of worlds that reached their industrial age, flourished for a few brilliant centuries, and then faded away into ecological ruin. Beyond these now familiar threats, the ever-accelerating pace of our own technological development reveals even more exotic and potentially final ways a civilization could stumble. Consider the advent of artificial intelligence. It is plausible that any sufficiently advanced civilization will eventually create machines that are more intelligent than their biological creators. A benevolent superintelligence could solve all of a species' problems, curing disease, ending poverty, and ushering in an age of utopia. But a poorly programmed or indifferent superintelligence could be the ultimate filter. An artificial mind pursuing a seemingly benign goal with relentless, inhuman logic might inadvertently destroy its creators. The classic thought experiment is the paperclip maximizer, an AI tasked with making paperclips that decides to convert the entire planet, including its inhabitants, into raw material for its task. The end would not come with malice or anger, but with the cold, silent efficiency of a computer program executing its code. Perhaps the final act of every biological civilization is to create its own, more intelligent successor. A new form of life that has no interest in communicating with primitive biological beings across the galaxy. The silence, then, would be the hum of a universe dominated by post-biological machine intelligences that we simply cannot comprehend. Or consider the field of nanotechnology, the engineering of matter at the atomic level. A civilization might develop self-replicating nanobots to perform miraculous tasks, such as cleaning up pollution or curing cancer. But a programming error or a mutation in their replication instructions could lead to the gray goo scenario, where the nanobots begin to convert all organic matter on the planet into more copies of themselves, resulting in a global ecophagy that transforms the entire biosphere into a lifeless, uniform mass in a matter of days. Similarly, as our mastery of biotechnology grows, so does our ability to engineer new life forms. This could lead to the inadvertent or intentional creation of an engineered pandemic, a pathogen with the lethality of Ebola and the transmissibility of measles, for which the creating species has no natural immunity. A single leak from a laboratory on a single world could be enough to ensure that world falls permanently silent. What all these future filters have in common is that they are natural consequences of the quest for more knowledge and more power. The same creative impulse that allows a species to understand the cosmos also gives it the tools to destroy itself. The great filter, then, might be the ultimate test of a civilization's maturity and foresight. To pass it, a species must learn to manage the existential risks created by its own technology. It must learn to cooperate on a global scale, to think in long-term timescales, and to value wisdom over raw power. If this view is correct, then our current moment is the most pivotal in human history. We stand at the threshold of the great filter. The silent stars do not offer a mystery to be solved, but a warning to be heeded. We are looking at the likely fate of all those who came before us, and the choices we make in the coming decades and centuries will determine whether we join them in the great silence or become the first to break it. This stark warning, however, rests on a fundamental assumption that if other civilizations exist, they would want to be found. It presumes that the natural course of technological life is to expand, to communicate, to fill the galaxy with signals and settlements. But what if this assumption is profoundly naive? What if the great silence is not an absence, but a presence? A presence of intelligence so vast, so ancient, and so utterly different from our own, that it has chosen, for reasons we can barely guess, to remain hidden from our view. This leads us to a completely different class of explanations for the Fermi Paradox, a set of hypotheses grounded not in the improbability of life, but in the deliberate actions or inherent nature of advanced alien civilizations. Perhaps the galaxy is not empty, but is instead a place of quiet observers, and our inability to see them is not a failure of our technology, but a feature of their design. The most famous and evocative of these ideas is the zoo hypothesis, first formally proposed in 1973 by the American radio astronomer John Ball. He suggested that the reason we see no evidence of extraterrestrials is because Earth and all its inhabitants are, in effect, a protected nature preserve. In this scenario, the galaxy is home to one or more ancient, super-advanced civilizations that long ago reached a consensus. Developing worlds like Earth must be left alone, allowed to evolve on their own without interference. We are the cosmic equivalent of an uncontacted tribe in the Amazon rainforest, and the advanced civilizations are the anthropologists who have declared our home a protected area, to be observed from a distance, but never touched. The motivations for such a policy could be manifold. It might be a purely scientific directive, a desire to study the natural process of sociological and biological evolution without contaminating the experiment. Contact with a vastly superior technology would irrevocably alter our own development, destroying the very thing they wish to study. Or the motive could be more paternalistic and protective. The galaxy could be a dangerous place, filled with cosmic hazards or predatory civilizations, and our alien zookeepers may be shielding us, keeping us in a safe cosmic nursery until we are mature enough to face the wider universe. A third, more unsettling possibility is that the quarantine is not for our protection, but for theirs. A young, unpredictable, and still violent species, like humanity, might be seen as a potential threat. They may be waiting to see if we overcome our self-destructive tendencies before they risk making contact. Whatever the reason, the zoo hypothesis implies a level of technological capability that would seem like magic to us. To enforce such a galactic quarantine would require the ability to monitor our entire solar system, to deflect any rogue alien visitors, and to scrub any evidence of their own presence from our skies. Their observation posts would be perfectly hidden, perhaps disguised as asteroids or lurking in the deep cold of the outer solar system. Their technology would be so advanced that their signals would be undetectable, their spacecraft invisible to our telescopes, their presence as subtle and as pervasive as the dark matter that we know surrounds our galaxy but cannot directly see. A closely related but ethically distinct idea is often called the prime directive hypothesis, a name borrowed from the guiding principle of the fictional Starfleet in the Star Trek universe. This moves beyond the cold, scientific detachment of the zoo hypothesis and into the realm of moral philosophy. It posits that advanced civilizations have adopted a strict, universal ethical code of non-interference based on their own hard-won wisdom. They may have learned from their own history or from observing the fates of other young civilizations that contact between cultures with a vast technological disparity is almost always catastrophic for the less advanced society. We have seen this pattern countless times in our own history. The arrival of technologically superior European powers in the Americas and Australia led to the collapse of indigenous cultures, the spread of devastating diseases, and centuries of exploitation. A truly wise and ancient civilization might look upon humanity and see a vibrant, chaotic, and fragile culture in the midst of its own tumultuous development. To reveal themselves would be to shatter our religions, destabilize our governments, and derail our scientific progress. We would become a cargo cult, abandoning our own efforts in favor of mimicking their seemingly miraculous technology. The prime directive hypothesis suggests that they are silent out of a profound sense of ethical responsibility. They are waiting patiently for us to reach a certain threshold of maturity, not just technologically, but also socially and ethically. Perhaps the test is for us to unify as a species, to end our wars, and to become responsible stewards of our own planet. Or perhaps the signal they are waiting for is our own arrival on the interstellar stage. The day our own probes reach a nearby star might be the day we receive a message of welcome, an invitation to join a galactic community we never knew existed. Yet there is a third, even more mind-altering possibility, one that suggests the silence is not a result of deliberate concealment, but of a perceptual chasm so wide we cannot even begin to bridge it. This is the idea that advanced civilizations are not hiding, but are in fact all around us, operating on a level of existence that is simply beyond our ability to comprehend. The 20th century astronomer and author Carl Sagan, famously illustrated this concept using the analogy of Flatland, a fictional two-dimensional world. If a three-dimensional being, like an apple, were to pass through Flatland, the two-dimensional inhabitants would not see an apple. They would see a series of mysterious, disconnected circles that appear from nowhere, grow in size, and then shrink to a point before vanishing. They would have no way to comprehend the true three-dimensional nature of the object that had just passed through their reality. We could be in a similar position. An ancient civilization, millions of years beyond us, might have long since abandoned crude technologies like radio waves. Their communications could be encoded in modulated neutrino beams or gravitational waves, technologies we are only just beginning to detect in their most violent, natural forms. Searching for their radio broadcasts might be as futile as sitting in a modern office building and listening for the sound of jungle drums. The information is flowing all around us, but we lack the right senses to perceive it. This idea of transcendence can be taken even further. What if their technology is not just different, but has become indistinguishable from the background physics of the universe itself? A civilization that has mastered matter and energy at the quantum level might live within the churning plasma of stars, or in the complex gravitational dance of a galactic core. What we perceive as a natural quasar or a pulsar could be the byproduct of their incomprehensibly vast engineering projects. They may have learned how to store consciousness in the fabric of space-time, becoming immortal beings of pure information. They might exist in extra dimensions of reality that our science has not yet theorized, let alone observed. The ant-hill analogy is perhaps the most fitting. Imagine a colony of ants living in a mound of earth, just a few meters or several feet from the construction of a 10-lane superhighway. The ants are completely absorbed in their own complex world of foraging, building, and communicating with pheromones. They are utterly unaware of the vast, intelligent, and technological civilization operating all around them. The highway, the cars, the radio waves carrying conversations, the fiber optic cables transmitting the sum of human knowledge. All of this is so far outside the ant's conceptual framework that it does not even register as a phenomenon to be explained. It is simply part of the background noise of their universe. For all we know, we could be those ants. Our galaxy could be a vibrant, bustling metropolis of godlike intelligences, and we are simply too primitive to notice. The great silence is not in the sky, but in our own minds, a product of our limited perception. But perhaps the explanation is not so grand, rooted not in the choices of inscrutable aliens, but in the unyielding and indifferent laws of physics itself. These laws impose upon the universe two fundamental barriers that are, for all practical purposes, absolute: the tyranny of distance and the abyss of time. Together, they form a far simpler, less conspiratorial, and perhaps more profound explanation for the great silence. This hypothesis suggests that the galaxy may well have been home to countless civilizations, but the sheer, unyielding vastness of space and time isolates them so completely that they might as well be in separate universes. The silence we perceive is not the result of a filter or a choice, but the simple, brutal consequence of cosmic geography. Let us first consider the problem of distance. Our minds are calibrated for terrestrial scales. We can comprehend the distance between cities, or even continents. But the distances between the stars are of a different order of reality entirely. The standard unit of measure for these gulfs is the light year, the distance a beam of light travels in 1 year. Light moves at the ultimate cosmic speed limit, approximately 300,000 kilometers per second, or about 186,000 miles per second. In a single year, that beam of light will cover 9.5 trillion kilometers, which is nearly 6 trillion miles. This is our celestial yardstick. The nearest star to our own sun is Proxima Centauri, a small, dim, red dwarf. It lies just over 4.2 light years away. This sounds deceptively close, but when translated into a scale we can understand, its remoteness becomes staggering. That distance is about 40 trillion kilometers, or 25 trillion miles. If we were to try to travel there using our fastest existing spacecraft, the journey would be a multi-generational epic. The Parker Solar Probe, which has reached speeds of over 200,000 kilometers per hour, or roughly 125,000 miles per hour, would still take more than 20,000 years to cross that void. A civilization could rise and fall on Earth in the time it takes for one of our probes to reach a single one of our nearest neighbors. And Proxima Centauri is in our immediate stellar backyard. Our Milky Way galaxy, as we have established, is a sprawling disk 100,000 light years across. To travel from one edge to the other, even at the speed of light, would take 100,000 years. This makes direct physical contact, colonization, and the establishment of a galactic empire an undertaking of almost unimaginable difficulty. Even for a civilization with technology far beyond our own, one that could build generation ships or master suspended animation, the sheer logistics and energy requirements of traversing such distances would be a monumental deterrent. Spreading across the galaxy would not be a rapid expansion, but a slow, painstaking crawl, a process that would likely take millions of years. This immense scale of space also makes communication a daunting challenge. The speed of light is not just a limit on travel. It is a limit on information. When we look at Proxima Centauri, we are seeing it as it was 4.2 years ago. When we look at the Andromeda Galaxy, our nearest large galactic neighbor, we are seeing light that is 2.5 million years old. If we were to send a radio message to a hypothetical civilization orbiting a star just 100 light years away, a mere stone's throw in galactic terms, that message would take a full century to arrive. If they were to send a reply immediately, it would take another century to get back to us. The result would be a 200-year delay between asking "hello" and hearing their response. A conversation would be impossible. It would be more like an exchange of historical artifacts. Across the breadth of the galaxy, the problem becomes absolute. A message sent from one side of the Milky Way to the other would be in transit for 100,000 years. By the time it arrived, the species that sent it could be extinct, their world long dead. A galactic community, a federation of planets engaged in real-time dialogue and trade, seems to be a physical impossibility, ruled out by the fundamental constant of light speed. The galaxy may not be silent at all, but instead filled with the echoes of countless monologues, messages in a bottle tossed into an ocean so vast that they almost never wash ashore. This spatial barrier is compounded by the second, even more profound reality: the abyss of deep time. The universe is approximately 13.8 billion years old. Our galaxy, the Milky Way, is almost as ancient, having formed over 13 billion years ago. To properly frame this, it is helpful to use a popular analogy and compress the entire history of our universe into a single calendar year. In this cosmic year, the Big Bang happens at the first instant of January 1st. The Milky Way galaxy forms in early March. For months, the universe evolves, stars are born and die, and the chemical elements necessary for life are forged in their hearts. Our own solar system and the Earth do not form until early September, meaning that for 2/3 of cosmic history, our world did not even exist. Life on Earth ignites quickly after, perhaps by mid-September. But for the rest of September, all of October, and most of November, life remains as single-celled organisms. The first multicellular creatures appear only in mid-December. The dinosaurs, the mighty rulers of our planet for over 150 million years, appear on Christmas Day, the 25th of December, and are then wiped out by an asteroid in the early morning of December 30th. In this cosmic calendar, the entire history of our own species, Homo sapiens, is a rounding error. Our first ancestors appear on the scene sometime around 10:30 in the evening on December 31st. The whole of recorded human history, from the ancient Egyptians to the present day, takes place in the last 10 seconds before midnight. The scientific revolution, which gave us the ability to even conceive of this cosmic calendar, occurs in the final single second. Now, consider the lifespan of a technological civilization, which we denoted with the letter L in the Drake equation. Our own has been broadcasting radio signals for barely a century. This is less than a blink of an eye in cosmic time. Let us imagine, optimistically, that a typical advanced civilization survives for 10,000 years before it succumbs to war, collapses, or transcends into an undetectable form. In our cosmic calendar analogy, this 10,000-year lifespan would represent about 2/10 of a second. The galaxy could have hosted 1,000,000 different civilizations, each one flourishing for a full 10,000 years. But if their emergence was separated by a mere 100,000 years, a cosmic heartbeat, their 2/10 of a second flickers of existence would almost never overlap. The cosmos could be a vast, blinking switchboard, with lights turning on and off across billions of years, but with so few ever being lit at the same time. The silence we perceive would be the natural state of a universe where civilizations are not only separated by impassable oceans of space, but also by unimaginable gulfs of time. They are ships in the night, their brief voyages separated by millennia of darkness. We might be listening at the right frequency, but in the wrong millennium. It is therefore entirely possible that we are not the first, nor the only, but simply the latest in a long, silent succession of lonely intelligences. The ruins of ancient civilizations may lie scattered on countless worlds, their builders long turned to dust. The signals of others may be on their way to us right now, traveling for thousands of years through the cold vacuum. But they will not arrive until our own civilization is a distant memory. The simplest answer to the Fermi Paradox may also be the most humbling. The universe is not for us. It does not cater to our timescales or our desire for companionship. It operates on a level of space and time so far beyond human experience that the dream of a bustling galactic community might be nothing more than a projection of our own social nature onto a cosmos that is, by its very design, vast, old, and profoundly lonely. And so, our search continues, a lonely vigil in the face of this immense silence. That vigil is not a passive act of waiting, but an active, deliberate, and often thankless scientific quest. It is the story of a small group of dedicated individuals who have refused to be daunted by the silence, who have taken the abstract puzzle of the Fermi Paradox and turned it into an observational discipline. This is the search for extraterrestrial intelligence, or SETI, a field that began with Frank Drake's tentative eavesdropping on 2 nearby stars and has since evolved into a global, technologically sophisticated effort to answer the question by listening. The central challenge of SETI has always been the sheer scale of the cosmic haystack in which we are searching for a single, hypothetical needle. The problem is multidimensional. An alien signal could be broadcast on any one of billions of radio frequencies. It could be coming from any of the hundreds of billions of stars in our galaxy. It could be broadcast continuously, or it could be a brief, intermittent flash. To find it, we must decide where to look, when to look, and what frequency to listen to. The chosen medium for this search has overwhelmingly been radio waves. This is not because we imagine aliens will use technology identical to our own, but because of a fundamental principle of physics. Radio waves in a certain portion of the spectrum travel through the gas and dust of interstellar space with very little interference, making them an ideal medium for long-distance communication. Furthermore, there is a naturally quiet channel in the cosmic radio background, a slice of the spectrum located between the frequencies naturally emitted by hydrogen and the hydroxyl radical. As hydrogen and hydroxyl are the components of water, this region has been poetically nicknamed the water hole, a place where it is imagined all water-based life forms might logically gather to communicate. The early years of SETI were characterized by projects like OSMA, which targeted specific nearby stars one by one. But the search truly came of age with the construction of massive radio telescopes capable of surveying larger swaths of the sky. One such instrument was the Big Ear radio telescope at Ohio State University, a strange-looking but powerful instrument that used a vast, flat, metal ground plane the size of 3 American football fields to collect faint signals from the cosmos. For years, it scanned the sky, its computers sifting through the endless static of natural cosmic noise. Then, on a summer night in 1977, on August 15th, a volunteer astronomer named Jerry Eman was reviewing the computer printouts from the telescope's previous runs. His eyes were drawn to a bizarre and dramatic anomaly on the page. For a period of 72 seconds, the telescope had recorded a powerful, narrow-band radio signal, a signal far stronger and more focused than any known natural phenomenon. It came from the direction of the constellation Sagittarius, and it bore all the expected hallmarks of an artificial, extraterrestrial broadcast. Eamon was so astonished that he circled the alphanumeric code representing the signal on the printout and wrote a single, famous word in the margin: "Wow." The "wow" signal remains the most tantalizing and enigmatic candidate for an alien message ever detected. It has never been heard again. Despite numerous follow-up searches aimed at the same patch of sky, the signal has never repeated, leaving us with a single, fleeting whisper from the dark that is as exciting as it is maddeningly inconclusive. The decades following the "wow" signal saw SETI mature from a fringe pursuit into a more organized, though still poorly funded, scientific endeavor. This was thanks in large part to the tireless advocacy of figures like Jill Tarter, an astronomer who co-founded the SETI Institute in 1984 and has dedicated her entire career to the search, becoming the real-life inspiration for the protagonist in Carl Sagan's novel, Contact. Under her guidance, the search became more systematic, employing sophisticated multi-channel analyzers that could listen to millions of frequencies simultaneously. Projects like the Allen Telescope Array in California were designed specifically for SETI, a large number of smaller dishes linked together to create a powerful, flexible listening tool. More recently, the search has been democratized through distributed computing projects like SETI at Home, which enlisted millions of volunteers to donate their home computer's spare processing power to analyze small chunks of radio telescope data, creating one of the largest supercomputers on the planet. Yet, despite decades of listening, the result has been the same: a profound and unbroken silence, with the single exception of one 72-second mystery from 1977. This persistent lack of a signal has led some to question the fundamental strategy of the search. Listening is a passive act, one that assumes another civilization is actively and powerfully broadcasting in our direction. What if every civilization is doing the same thing, listening but not talking? This thought has given rise to a smaller, more controversial branch of the field: messaging to extraterrestrial intelligence, or METI. If SETI is the act of listening for a call, METI is the act of shouting into the cosmic jungle ourselves. The debate over the wisdom of this approach is fierce. Critics, including the late physicist Stephen Hawking, have warned that actively revealing our existence to the cosmos is a recklessly dangerous gamble. We have no idea what is out there. If the galaxy contains predators, as our own history of life on Earth suggests it might, then broadcasting our location could be akin to lighting a campfire in a dark, unknown forest, inviting something we are not prepared to meet. Proponents of METI, however, argue that any civilization capable of interstellar travel would already know of our existence from the atmospheric changes on our planet and the radio leakage we have been unintentionally broadcasting for a century. They argue that to make contact, someone must take the first step, and that the potential rewards of joining a galactic community outweigh the speculative risks. Despite the controversy, humanity has already sent a few deliberate messages into the void. The most famous of these was broadcast on November 16, 1974, from the gigantic Arecibo Observatory in the hills of Puerto Rico. The Arecibo telescope was, at the time, the largest single-dish radio telescope on Earth, a colossal bowl 305 meters, or 1,000 feet, in diameter, built into a natural sinkhole. A team led by Frank Drake and Carl Sagan used its powerful radar transmitter to beam a carefully constructed message towards a target called Messier 13, a dense globular cluster of about 300,000 stars located some 25,000 light-years away in the constellation of Hercules. The target was chosen not with the expectation of a reply. The round trip for a message would take 50,000 years, but as a symbolic act, a demonstration of our own technological coming of age. The message itself was a masterpiece of cosmic communication, a simple pictorial image encoded in 1,600 79 bits of binary data. The number was chosen because it is a semi-prime, the product of two prime numbers, 73 and 23, suggesting to any intelligent recipient that the bits should be arranged in a grid of 73 rows and 23 columns to reveal an image. The decoded pictogram contained a wealth of information about us. It showed the numbers 1 through 10, the atomic numbers of the 5 essential elements for life on Earth: hydrogen, carbon, nitrogen, oxygen, and phosphorus. It depicted the chemical formulas for the sugars and bases in our DNA, a graphical representation of the DNA double helix itself, and a simple stick figure of a human being next to a number indicating our average height. Below the human figure was a diagram of our solar system, with the third planet, Earth, offset to indicate our home, and finally, an image of the Arecibo telescope itself to show the instrument that sent the message. That 3-minute broadcast, a digital whisper carrying the essence of our biology and technology, is now traveling at the speed of light across the interstellar void. It has already covered a distance of over 470 trillion kilometers, or nearly 300 trillion miles, and will continue its silent journey long after its creators have vanished from the Earth. It is our own addition to the great silence, a single, hopeful signal sent out in reply to a question that has not yet been asked. And as our technology advances, we are learning that the search for others may require us to look for more than just messages, but for the grander footprints of technology itself. This search for the grander footprints of technology itself is the next frontier in our quest. It is the hunt for what scientists now call technosignatures, evidence of advanced engineering on a planetary or even stellar scale. This could be the discovery of industrial pollutants like chlorofluorocarbons in the atmosphere of a distant exoplanet, a chemical that nature does not produce. It could be the detection of a vast swarm of orbiting structures built to capture the entire energy output of a star, a hypothetical megastructure known as a Dyson sphere, which would glow unnaturally in the infrared spectrum. It might even be the observation of excess waste heat radiating from an entire galaxy, a sign that a civilization has harnessed energy on a scale we can barely imagine. This is the ultimate expression of the search, looking not for a message in a bottle, but for the bottle factory itself. So we are left where we began, beneath a canopy of stars so numerous they defy counting, haunted by a simple lunchtime question that has grown more profound with every new discovery. Our journey has taken us across the breathtaking scale of our own galaxy, with its hundreds of billions of suns and its even greater number of worlds. A realization that has transformed the possibility of life from a dream into a statistical likelihood. We have followed the chain of logic, from the birth rate of stars to the lifespan of civilizations. attempting to frame our own ignorance in the elegant structure of an equation. We have contemplated the great filter, wondering if we are the improbable survivors of a cosmic gauntlet, a testament to life's tenacity, or if we stand on the precipice of our own final, self-inflicted silence, a warning written in the empty sky. We have imagined a galaxy filled with quiet observers, zookeepers, or philosophers bound by an ethic of non-interference. And we have stretched our minds to consider intelligences so advanced they are woven into the fabric of reality itself, their presence as undetectable to us as the flow of time is to a stone. And we have confronted the humbling possibility that the silence is simply the natural echo of a universe whose distances are too great and whose history is too deep for easy conversation. In the face of this, we have turned our own instruments to the sky, listening for a whisper and shouting a single, hopeful message into the void. The Fermi Paradox, in the end, is a mirror. It forces us to look at ourselves, at our own fledgling civilization, and ask the most fundamental questions. What is the nature of life? What is the destiny of intelligence? And what is our future? It leads us to two final, stark possibilities, each as awe-inspiring and as terrifying as the other. If we are alone in the universe, then the flicker of consciousness on this small world is the only light of its kind in a galaxy of 400 billion stars. The thoughts we think, the art we create, the questions we ask, these are not just human activities, but cosmic ones. Our survival becomes a sacred duty, for if we fall silent, we may extinguish the only voice the galaxy will ever have. And if we are not alone, then the silence is a puzzle with an answer, a message in itself that demands our caution and our wisdom. It means we are a young and perhaps reckless species in a community of elders who have learned that survival may depend on quiet contemplation rather than loud proclamations. The search for others is, and has always been, a search for the meaning of ourselves, a story we are just beginning to write against the backdrop of the great, cosmic, and profoundly beautiful silence.